Alright, hello everybody, this is Les Hall with another quick 5-minute video on some work I've been doing. Let me show you first an illustration. Let's look at this illustration. This is some 3D printed work that I've been doing. Down here with the hangnail, you see a laser pointer that I'm holding down with my grubby fingers onto a plastic 3D printed object, which enables me to crudely position the laser pointer so that it strikes a 3D printed lens here on the edge. This light now travels through the lens and it strikes a back plate in white that was going to be a lens, but I'm using it now as a striking surface. And here you see where the main dot has stretched wide and gone closer inward. And then, most importantly, you see these tails. This one tail here and this one tail here that go far further to the, well, up as the photo is positioned, but to the right as you look down on the travel. And what this says, I think, I'm not sure, but you see, if we only had the particle model of light, that light should go straight through or get diffused and spread out a little bit, but these tails are not explained by that. So I think we're looking at the other aspect of light, which is the wave nature of light. And if you can't really, maybe you can see a little bit. The lens is conical in nature with a hole in the middle, much like this one is, and it's stepped. It's stepped. So it's hard to explain. Suffice to say that regardless of what's going on, this lens is acting a little bit like an optical lens, which the big conclusion here is that it is true what people say, that you can't 3D print optics on a conventional FDM printer. However, it's also true that if your goal is not to create image optics, but other types of optics, then you can print things. And that's what this photo shows. This illustration here shows the classic Pink Floyd prism with theta 1 and theta 2, index of refraction 1, index of refraction 2, and Snell's law here. If we apply that to another shape, such as a rectangle, instead of a triangle. See, 3D printing, you would get a stepped nature to this triangle. But in 3D printing, we can closely approximate a rectangle. Then here we have 3 light rays coming in at roughly the same, at basically the same angle. And I've crudely traced their path through this cube using Snell's law in each case. And what happens, interestingly, is they come in at theta 1 and they exit at a theta that is less than or equal to theta 1. So the square lens, or cube lens as it were, or a ring with a square cross-section, actually acts as maybe a light focuser or a light straightener, in a sense. Okay, so that led me to this design. And here we have, sort of looks like an onion. This shape here is a sigmoid in shape. That is over here 1 over 1 plus e to the something. You know, and that's the sigmoid function. And I use that function to create this shape where all of the internals go up into the top. We have some bracing here. And there's actually a bottom layer, 2 or 4 printed layers thick. It's intended to be printed in 100 micron layers. At the top, we have the exit situation. And the idea is that light will enter here in all kind of directions, crazy directions from, say, a flashlight, or a halogen light, or some other very bright source, such as a arc welder, you know, something really bright, and will produce with a lot of optical energy, enters here. Some of it stays internal, some of it stays bouncing around between them, but some of it gets bent in a straight direction. Presumably this will capture that light and reduce it down to a stronger focus here where it will exit, possibly melting the PLA here, or just because of the diffusing nature of the PLA that I'm using, it's semi-transparent, possibly just lighting it up, which in and of itself is cool. But what we really are looking for is for something clear, 3D printed, that will do the job of concentrating the light into a beam. And with the information that I presented to you in this video, you can come up with many, many structures that accomplish that goal. Why would we want to accomplish that goal? Well, we can perform, if we can send a very strong beam of light out of a light source. We can communicate by modulating it. We can illuminate things from far away. We might be able to warm or even heat up things from far away. And close up, it may be a focusing technique that will take light from a very strong source and bring it to a beam that will do industrial functions. Or you have the basis of a ray gun or similar type of device. Yeah, so I kind of gather that this or other stuff like this, like the lenses I showed you, are the basis of the way optical weapons work. So, having said that, I'm going to close the video, and I guess I went over 5 minutes, so be it. It was important stuff to say. And now it's been said. So, less out, praise the Lord.